Now let's take a look at what's called an aldol condensation reaction. So when we have our aldehyde here under basic conditions, we will form the beta hydroxycarbonyl compound that looks like this. So we have 1, 2, 3. We have our alcohol there. And we would have a methyl group there. So do we see how it's the alpha beta? Sorry, I keep saying alpha beta, sorry. The beta hydroxycarbonyl compound. We have our alpha and our beta. Do you see that? Now, do you see where the parts are coming from? Right here. So they're both of these. How many carbons do we have total? 1, 2, 3. But how many do we have over here? 1, 2, 3, 4, 5, 6. So you can see that we're reacting this molecule with itself. And I'm going to show you the mechanism of that momentarily, okay? But what's different between an aldol reaction and an aldol condensation is the fact that in an aldol condensation reaction, you're adding heat. And so what happens is you first make the beta hydroxy carbonyl compound. That's what you first make. And then, because there's heat added, it doesn't stay and stop here. It turns into this. The alcohol right here on the beta carbon goes away and is replaced with a double bond like that. So that's still our alpha, that's still our beta carbon, but you see how there's a difference now? And this compound is called the alpha beta unsaturated. And blue marker is running out. Alpha beta unsaturated carbonyl compound. Okay, so that's what a condensation reaction is. It's going to take two molecules, two of these, and join them together, and in that process, you lose a smaller molecule. And what's the smaller molecule that's being lost? Well, it's the OH that's leaving. Okay, and in essence, water is going to be that small molecule that has left. Okay? Now let's evaluate, why is this called an alpha beta unsaturated carbonyl compound? We still have a carbonyl right there. And then at the alpha and the beta positions, we are missing two hydrogens. So it is unsaturated. So that's where the name comes from. Okay, so the mechanism. So from here to here, the mechanism is just the same from the previous video. But let's do it just to get practice, shall we? So what happens is that we are under basic conditions. So I'm going to represent the sodium hydroxide like that. And it's going to come in and abstract the proton. But which one? Well, the aldehyde hydrogens are not acidic. It has to be hydrogens that are on the alpha carbon. And so that hydroxide is going to come, abstract that proton, and generate ourselves the enolate. Now this is all reversible, right? So that would be called our proton transfer. So that's our proton transfer step. So we'd get our enolate. Like that. And that's going to react with another aldehyde right here, but this time it's not going to be protonated, charged. So we have electron-rich species, and electron-poor species. And so that's going to be a nucleophilic addition. There's our nucleophilic addition step, because what's going to happen? That lone pair is going to come in and do that. Now here lies the challenge, okay? Trying to keep it all straight. We're keeping the connectivity here. So what we can do is number carbons if you'd like, or you can, for what I'm going to do, I'm just going to leave this molecule the way it's shown. I'm just going to draw it, okay, like this. And what has happened here? I have taken pi electrons and moved it onto the oxygen. So there's already 2 lone pairs, okay? But now there's going to be a third one. So that's going to be a negatively charged species. Now, what has happened here? This carbon right here has formed a bond with it. So this is going to look a little messy at first, but we can clean it up. So this carbon forms a bond with that carbon. So I'm just going to draw it down like that. So that carbon that I'm pointing with my left hand right here is that carbon, okay? And we see that it's attached to this carbon right there. So maybe we should number these. Let's do that, okay? So let's see, how do we want to do this number-wise? We'll go 1. Let's go 1, 2, 3. Okay, and that would make that guy 4, 5, and 6. So this is 4, 5, and 6. And we just said that carbon 2 formed a bond with carbon 6. So we'll call that carbon 2. And what is carbon 2 also bonded to? We see that it's bonded to what? Carbon 1. We'll call that carbon 1 there. And then it's bonded to the carbonyl with carbon 3. So we would come here, draw carbon 3. But what's attached to carbon 3? And the hydrogen like that. Catching that connectivity there? And then what's going to be the next step? We're going to have a proton transfer. And what's that going to proton transfer with? Well, we have, after this proton transfer step over here, what did we generate? We generated some water. And we already have water in our reaction, but we did regenerate some more water there, so we can use that one. And then what's going to happen? We will do a proton transfer. I'll just come, grab that, like so, and give us our first product, the beta-hydroxycarbonyl compound. Draw it like this. Then we have this guy, boom. Now let's number this so we can see where everything's at. So we have 4, 5, and 6. 1, 2, and 3. So what we can do is just take this molecule and just rotate it and spin things around to make it look like this. So we can see 4, 5, 6, 2, 3, and 1 right there. And so that's what our beta-hydroxycarbonyl compound looks like. And so this mechanism right here is exactly the same from the previous video, okay? But if we wanted to go into reverse, remember how if this was the only thing that we're given and the instructor says, okay, here's the product that I want, what are the starting materials? Remember, we just sever between the alpha-beta bond, Separate those two pieces, and you will see that when you separate those two pieces, you come up with this structure right here. So that's the first part of the mechanism. But remember, whenever there's heat added, it cannot stop right here. It is going to go to this. And so I need to erase this board right here so we can look at the mechanism from the beta hydroxy carbonyl compound to the alpha beta unsaturated carbonyl compound. So the next step, we realize that we are still under basic conditions when we've made this. And so when I take a look at this molecule here, we still have a hydrogen on that alpha carbon. And alpha hydrogens are acidic. So we can invoke a proton transfer in which we're going to deprotonate that proton. So we're going to do a proton transfer, and we're going to invoke our hydroxide right here. So that's going to come and form another enolate. Okay, so that's going to come, grab that, put the electrons on carbon 2. So I'm going to draw that molecule over here just to give us some more space to work with. Like that. And we still have the carbon there. Let's make sure we're numbering everything so we keep track of what's happening here. So we have our enolate there. Now, why is this enolate form? Why is it so good? Because it is resonance stabilized with that carbonyl. So that enolate's can be generated with relative ease. That proton right there is going to be relatively acidic because of it being the conjugate base is resonance stabilized. So let's take a look at the numbering system here. Let's keep it consistent. 4, 5, 6. And then that's 2, 3, and 1 still. Okay, now we have an enolate there. So what's going to happen next here is something really interesting is that we have a step here that we can term a heterolysis step. We could refer to it as that. But look at the mechanism that I'm going to invoke here and see if that raises some eyebrows. I'm going to take that lone pair right there. I'm going to bring it and snap it between carbon 6 and carbon 2. And when I do that, that's going to make the alcohol leave. So that's going to give us our product. Right there. And what left? Our hydroxide molecule right there. Now that should raise eyebrows because previously we've said, hey, alcohols are horrible leaving groups. Why are you saying this works? Some people might be like, hey, this is almost like an E2 mechanism here, where we're making it just eliminate. It's not really quite that mechanism as well. The mechanism name for this step right here, we could call it a heterolysis because the group is leaving, but we could also call it a E1CB mechanism. Okay? And the E stands for elimination. The 1 stands for unimolecular because we're just dealing with one molecule right here. And the CB stands for conjugate base. And so that turns into our base right there. See that? So this is technically a E1CB mechanistic step. And so that's still, just because I'm telling you this is a different type of mechanism, still doesn't rationalize in your mind probably is, well, why can the alcohol leave? I thought you said it can't leave. Well, it comes down to the fact that we have to look at the whole process. And we can see, okay, yes, it's high in energy to make a alcohol leave. But what do we get at the end? We get a conjugated system here. So we have that double bond right there is conjugated with that right there. And because we generated a conjugated system, that really overcompensates for the horrible leaving group that the alcohol is. Yes, it's still bad leaving group, but it can leave in this E1CB mechanism because we generate a species that is conjugated, and that just overcompensates. Granted, we're also adding some heat, so that helps. So we're adding heat, we're getting a conjugated product, and all that combined allows the alcohol to be an okay leaving group. And so if we want to finish and make sure we have this all numbered right, this would have to be 4, 5, the beta carbon is 6, the alpha carbon is 2, 1, and 3. Okay? But you see, in every step here, what is it? It's reversible. So your instructor could very well say, okay, here's the product that I want you to make. How do you do it? What is the starting materials? So I want to show you how to do that. So we'll clean up the board. So if that's your alpha beta unsaturated carbonyl compound and you need to know what starting materials you need to use, we need to establish where's our alpha carbon. So we find our carbonyl, that's our carbonyl, the adjacent is alpha, then the next one is beta. And then we, just like for the aldol reaction, we just sever between the alpha and the beta. And I'm going to take this piece right here on my right and just draw it as it's shown right here. I have a carbon down, boom, boom, H, carbonyl. Okay? So when I sever that double bond right there, I'm just getting, what I'm really doing here is I'm just replacing that double bond right there with the hydrogen. Getting one more hydrogen there. Let's see. How many hydrogens are on this carbon? 1, 2, 3. So there's 0 hydrogen. So what we actually have to do is add 2. Okay? So that piece, when I take this bond now and just bring it up, do you see how this representation right here is that representation? And do you see how this matches? Okay? So being able to look at the molecule in different ways. So what do we do when we sever the alpha-beta bond, carbon-carbon bond? On the alpha carbon, we add in 2 hydrogens. Now, when we take a look at the beta piece, what I'm going to do is 1, 2, 3. I see that there's 3 carbons, like so. And so what are we going to do to that beta carbon here? So we'll call that our beta carbon. Just trying to match it up here. What are we going to do? We're going to just add on our double bond O. And then we have to tack on our hydrogen right there. And so then you could say, hey, that piece matches that piece. Now this isn't going to be the case every single time. These 2 pieces can be different depending on what your product looks like. And when the 2 starting materials are different aldehydes, we call that a crossed aldol reaction. So that discussion is for another video. But when your 2 species starting materials are the same, that's just a normal aldol condensation. Or if there's no heat, that's just a normal aldol reaction. But when they're different, it would be called a crossed aldol if there's no heat. And if there is heat, it would be a cross aldol condensation.